Hello again. We're here in time for our next lecture, and I'd like to spend the next number of minutes discussing with you the approaches that could be taken to characterize polymeric materials in ways that extend what we saw in the earlier lecture related to spectroscopic characterizations, and to actually spend a little bit of time thinking about what is the nature of materials of this type that make them special and present with a form of complexity that is unique to this form of matter. So by definition, this is a very incomplete list of approaches that can be taken to characterize polymeric materials. But having said that, let's jump in and see what we can find. Well, first and foremost, I said polymers are a special class of matter. So, what are they? They're and basically, they're most commonly very large organic molecules, and all of the slide says from hundreds to thousands of atoms. I think it's probably safe to say if a polymer was only thousands of atoms long, it is probably, even for all intents and purposes, even though it's a very big molecule, it might not even be a very interesting system from the perspective of an application in technology. Some macromolecular structures are in fact enormously large molecules. And in fact, we can think of important examples where the molecules approach essentially infinite molecular weights, and such that we might say at that limit, the entire sample is one single macromolecule. And of course, I'm thinking about densely cross-linked materials, as you might find, for example, in the epoxies that are used as the resin phases in advanced composites, carbon fibers with epoxies to generate a really high strength to ratio, high strength to weight ratio materials that are used, for example, in the manufacture of modern high performance jet aircraft. Okay, so having said that, we know they're big molecules. How do we classify them? And and we could actually think about this in a number of contexts. For example, because there's so many different kinds of polymers. Thermoplastics, so-called thermosets. Things that, because of the way in which they're processed or cured, change bonding characteristics. Materials that have unique and interesting mechanical properties. For example, elastomers, a material that we use a lot in our research in a variety of contexts. But let's actually launch into this and see what we mean. The most simple forms of polymers are ones that actually have, and I have to apologize, these are really bad structural drawings, which I've taken off of the internet, and obviously if I knew how to use ChemDraw and things like that, I could have drawn these things in much better projections of actually what their underlying structures are. So anyway, polymers can be represented by 3D models, ball and stick figures, 2D models. But essentially all these depictions are ones that are meant to show things related to underlying structural and compositional attributes that are present in the molecule. And all these examples that are shown here more or less correspond to polymeric systems that are comprised of long single chain organizations, and many polymers are much more complicated than that. All right, so we know that things involving carbon in particular, have geometric characteristics. We know, for example, carbon-carbon single bonds are able to rotate around those bonds. So conformational dynamics will be part and parcel of the way polymers work. So it's not like they're a rigid, locked-in kind of thing, but rather things that flexibly and adaptively respond to the environment that they're in, and perturbations that are to which they're subjected. Finally, on this slide, they're shown, something that's not the polymer, but rather, the monomer from which a polymer might be described. And in bad structural form, those are two depictions, or at least alleged depictions, of the monomer styrene from which we would construct the molecule polystyrene. So polymers are then takes monomers and they're linked together, and they're built up from repeat units of these monomers, and in the sequence shown, ethylene, the C2H4 molecule, is converted to the very large macromolecule polyethylene via the conversion of a pi bond to a carbon-carbon sigma bond. And that reaction is net exothermic. And that's actually a really important point. Why does it need to be exothermic? Well, when we go from lots of small molecules to one great big gigantic molecule, it needs to be exothermic. Otherwise, entropy would dictate it would be very, difficult to make one big molecule at the expense of lots of little ones, and so the stronger bond strengths make these systems that spontaneously would want to go to the long chain configuration, given a pathway to get there, and that's a really important part of a course that would be taught in polymer chemistry and materials chemistry. How bonds of that type can be made very efficiently to form very high molecular weight materials. Okay, but what is it that we have to think about when we're going to talk about the nature of this very big long chain molecule? And let's think about, just a simple case of what's shown here, a polyethylene molecule, where I take lots of monomers, the C2H4 moiety, and stitch together all these carbon-carbon bonds to make a really gigantic molecule. And more importantly, how does the chemistry work when I put this all together? When I make this really big molecule, is it in fact a molecule, or is it more in fact some complex mixture of molecules? Do I actually put together 10 ethylenes, to make a decaethylene, or is it a nonaethylene and a undecaethylene? What happens? Do I make a discrete thing? And this is actually an important point about the nature of essentially all synthetic polymers. So I'm a human being. At least I like to think I'm a human being. I'm alive. At least I like to think I'm alive, and I embed within myself lots of macromolecules, of a biological form. And the thing about the biological macromolecules is that, excuse me, the way these are made in living systems tend to build the macromolecules with very high precision, such that they rigorously perform the function for which they're designed. They're highly functional molecules, and all the pieces have to be put together in such a way that you wind up with a more or less discrete structure, which has the property expected of a particular enzyme that's needed, in a pathway that would be essential to keep you alive. And that's where biological systems differ from wholly synthetic macromolecules. Like when we're making polyethylene, a catalyst system may stitch together 19 of them, on one reaction sequence, and do 27 on another, and do 13 on another, and do 373 on another, and basically, that the chemistry is eliciting, combinations, but may in fact not get to a discrete and single numbered endpoint. And what I'm saying here in complicated form is that synthetic macromolecules are always characterized by a distribution of molecular weights. And that turns out to be one of the most important properties about these kinds of materials. And as a result, one of the most important things that people generally want to know is what is the nature of that molecular weight distribution. And the reason why they want to know what is the molecular weight and also what is the distribution of molecular weight. So obviously what you're going to determine is an average molecular weight and the breadth of the distribution that defines that average value. And the reason why you want to know things like that is that if I take that sample and I dissolve it in a solvent, the properties of those solutions vary in accordance with differences in the nature of those molecular weights and their distributions. The properties of a melt would vary as a result of the characteristics of the average molecular weight and its distribution. And so it's important to have approaches that let you determine this. Well, this is actually determined in a number of statistically relevant ways. And there's two molecular weights I could point to as average molecular weights that have important meanings. And one is, what is the number average molecular weight, right? And that's the molecular weight that corresponds in a distribution of molecular weights, as is shown in the slide, that you have the same number of molecules above and below, right, that average value. And the weight average molecular weight, where you have the same amount of mass on one side or the other of that average. Okay. So the word weight here is not actually, a good thing. So but it is in fact the thing that's used. So the molecular weight and the number average is just basically, a summation of all the individual components and in such a way that, we normalize this distribution and factor this distribution in terms of the value n, the number of molecules. And whereas, the weight average is done in the context of the mass component. So in a book on polymer chemistry, you'll find discussions of the statistical basis by which these kinds of analyses can be done and the reason why they're important. But there are also outcomes that are reflective of the nature of the chemistries that put them together. And for example, certain forms of polydispersity always accompany particular ways of forming macromolecules, like for example condensation polymerization, living polymerizations, free radical polymerizations. Each of these techniques give outcomes of molecular weight distributions that are very different and scale in complex ways with the magnitude of the molecular weight, how large a molecule we make, right? Because these are statistically determined. So in your slide set, I've put some examples that illustrate, like how you might, in a simple sense, use data of this type, to go ahead and calculate these kinds of parameters. But the point is, how do you populate a table like this and find out things that, look like, what's actually shown there, and that, this is, a conceptual example, but how would you, in fact, actually measure something to tell you how these systems have, features like this? And another part of it is we can also talk about other descriptors, and one you'll hear people discuss is the degree of polymerization. And just as there is a number average molecular weight and a weight average molecular weight, the degree of polymerization is essentially the value of n that we talk about as being the size of the molecule based on a number of monomer sequences that have been stitched together. But here reference to whether or not we're talking about the number or mass based averages for that system. So, n is basically a measure that tells you pretty much like how many monomers have been put together. And you notice that like for example, polyvinyl chloride. It's a fairly simple polymer. If I have molecular weights of 20,000. Right, we're only talking like on the order of less than 400 monomer sequences that have been put together to make that that macromolecule, right? And obviously, industrial polymers and technically technically important polymers might have molecular weights that are in the millions, right? And so those would actually correspond to cases where a lot of chemistry has been done to make very large molecules. Well, all right, so let's talk about an experimental basis by which we might be able to determine something about, what these distributions look like. And actually, some of the most important ways of doing sizing are ones that are based on molecular approaches to sizing. And the most important of which, I guess I would have to say the most important of which is gel permeation chromatography. And here we have a material that has various kinds of interstices and interstices of various size and dimension, extent, and continuity through the solid. And as the cartoon shows, basically all you do is you think about how it is that objects of different size might actually interact with and translate through a region that contains all these interstices. And so if you look at the slide, you'll notice that the little red dot, can kind of get lost into the interior, and this great big blue guy, he can't get in there at all, and so there's volume elements in if we had a column of this stuff, with this kind of mesoporous type of architecture. There's volume elements from which certain components in a mixture like this would be excluded, and other components would be able to get lost and otherwise while away the time in such a way that if I have a flow and I sweep things through, whereas the flow only exists in the region external to this mesoporosity, the blue things get swept out very quickly, and the things that are lost in the interstices, where the motion is only diffusional, and hence the fluids are stagnant in those places, they take longer to come off. Right? And so basically what you see in a slide such as this is that material goes onto the column. It begins to rattle through. The things that get lost in the interstices get hung up on it. But, the big things will then eventually come out when sufficient fluid has been pushed through the column. But it's the big ones that elute first and the small ones that come out second. And if we have a way of detecting their exit from the column, okay, we would actually then be able to see an elution diagram that would tell us when things had passed off, and they would separate according to size, right? So that's the simple cartoon picture. Now, having performed an experiment like this, all right, they separate according to size, but how is it that I know what that size is? I mean, so I've got parameters. I know a dead volume. I know I know things about when the injection was done. I know different regimes of the evolution of this elution chromatogram. So, like, so for example, in the B region, that's when stuff's on the column, and then C corresponds to the times when big things come off, and D where the little things come off, and I can say things about the column, but I still don't really know anything about size explicitly. Well, this technique is one that benefits from and exploits the ability to make well-defined standards. And basically, what we do is we can relate this measurement, which is based on this idea of the excluded volume, by looking at how known standards elute from a given column. This actually is one of the things, and I'll warn you, if you have friends in your research environment who depend upon this kind of chromatography for a living, and you ask to do a separation on their column, they will probably, become ugly. And the reason why this is that once you calibrate a measurement like this, you never want to do anything to goof it up. And the worst thing you can do to a person is to goof up this kind of measurement protocol. So they usually will tell you, no, you can't use it. Unless they're very, 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 very nice. And if you do goof it up, they'll hate you forever. But you will have to then do the hard work to fix the problem. So the references here are everything, and when you perform the references, you can then in fact say where it is that your unknown fits on the known elution profiles of these known standards. And then the standards can be characterized, via complementary methods, usually by a lot of work. But then the unknowns are then characterized in a much more simple way by comparison with the standards, using relationships such as shown schematically in the slide. Okay. And the parameters that are needed to do that are just basically taken off of the elution chromatogram. And finally, I'll say that there's one other component in it, right? And that is we also not only look at what the elution profile looks like, these times, how long does a thing stay on the column, which is saying something about time, but we also look at the line shape of the component eluted from the column. So, for example, the line shape is one that reflects not only how long a sample has spent on the column, but it also reports on the polydispersity of that sample. So, for example, if I have a polystyrene, such as shown here, with a particular molecular weight, the elution of that from a calibrated column is going to be characterized by an explicit line shape that's unique to that experimental circumstance. And when I analyze an unknown of similar molecular weight, and if I find that the line shape is narrower or it's broader, that means that in fact the polydispersity index is different. And there's ways in which that can be quantified based on that comparison to a standard. If you look on the right side of this slide, you notice that there's an elution characteristic for a polystyrene, 24,000 molecular weight, but with a polydispersity index almost of 5. This is actually a very broad distribution of molecular weight. And actually, when you look at this, the reason why the polydispersity index is so large is that it's actually eluting as two components. And this comes from the fact that this is a polymer made by free radical polymerization. And the way the mechanism of this reaction works is that when we make polymer, it grows by a chain propagation step where the molecule is becoming larger and larger. And then at some point, it kills itself. And it kills itself either by two of these propagating radicals combining. So we have, two radicals of some average size that when they combine and kill two radicals, you now have one molecule that's twice as large. Okay. And the other thing they can do is they come together in bimolecular form, but one shoots out a hydrogen atom to the other, forming an olefin on one chain and a saturated alkane type CH bond on the other. And that's called disproportionation. So those two radicals terminate each other, but leaving behind two molecules of identical molecular weight, plus or minus the proton. Okay, so and those give, and of course that must be a kind of reaction scheme that generates very broad distributions. Polydispersity indexes, which is a measure of how wide the distributions are, never get to be much better than about 1.1 or thereabouts for most synthetic macromolecules. And in those instances, they would have to be made by living polymerization mechanisms where the growth steps for the chemistry follow what's called Poisson statistics. And so in a materials chemistry course, you would study things like that to understand why that's true. Now, there's other ways in which we can characterize the size of macromolecules. And actually, one of the really powerful ways of doing it was actually recognized by a Nobel Prize in chemistry not so many years ago. And part of the discovery here that was really important was not the fact that we figured out how to make mass analyzers that could work on very big molecules. It was the discovery of how you can get very big molecules into a mass analyzer. And that's like not a non-trivial problem. And there's a lot of different ways that it can be done. So for example, electrospray ionization is one way of doing it. Another way of doing it is so-called matrix-assisted laser desorption ionization. So basically what these are so-called soft ionization techniques in which large macromolecule is brought into the gas phase via a physical process that also attaches a charge to it. And in that way, we can then use the electric field based dynamics of mass analyzers to measure charge to mass ratio in a variety of ways. So the schematic that's shown on this slide is a so-called MALDI time of flight mass analyzer, which distinguishes charge to mass ratio by the length of time it takes something to go from, basically the front end of the mass analyzer to the detector at the back end. So it's that's where the word time of flight comes from. So and so the velocity scale as both the mass, right, the mass and charge. So if we attach one unit of charge, one positive charge to a molecule of mass m, and another unit of charge to a different molecule of mass 2m, the one that's twice as large will take a longer time to reach the detector, and hence we can relate that signal to the quantity and specific mass of components that are present in the sample. And this is a physical description of the MALDI experiment. And and as I said, there's other approaches, but this one's exemplary. And so what we do is we have a sample substrate. The material of interest is placed on this substrate. a matrix material is applied to it. These are compounds which are which are subject to photo degradation by, in this particular case, a pulsed nitrogen laser, irradiating it at 337 nanometers. Right, the matrix material being sensitive at that wavelength, whereas most of the materials of interest, for this for the kinds of analyses that we care about, would not be. And the excitation event with that laser leads to the decomposition of the matrix, a little puff of explosion, which also attaches a charge to the molecule. Right, and once it's charged, it then can be pulled into the mass analyzer via the electrodynamical fields that are used in this instrument and mass analyzed by time of flight. Now, this is a technique that's capable of really fantastically high resolution, and I mean fantastically high resolution in the sense that large operating dynamic range, so you can get to really large masses, but you can measure really large masses with very high precision as to what their actual mass is. Okay, and so I show here an example of a sample that has a number average and weight average molecular weight of 51, 57, 52, 27, polydispersity index of 1.1. So this is a really monodispersed sample of really high order, profoundly good sample. And you notice that the sequence of 58 grams per mole actually reports on the character of this monomer sequence. And I like, when I teach this class in Illinois, ask the kids, have you encountered or in any way used this polymer today? And most of you all would say, oh. and I would like to say I hope you have, because it's actually a kind of thing that would suggest something about hygiene, because it's used for example in shampoo and a variety of other applications. You can find it in cosmetic formulations, etc. Right, but it is the kind of thing that you find in things that are typically used for cleaning in various sundry ways. So ubiquitous material. But here we see that in point of fact, we actually see the charge to mass characteristics of all the things that are present in the sample. This is not the fragmentation of the molecule. This is actually the amount of material, right, that's present with all these different discrete masses. And we can actually use this data to construct the polydispersity index type level analysis that's shown here, just by actually quantifying what's seen in the mass spectra. So that's very powerful. Now let's go on to other aspects of structure, that might be a little bit more complicated. So we've been drawing structure to this point as just being linear sequences of monomers. And so monomers can go together, here indicated by little balls, as a linear sequence, just one ball following another. But we can get things going together with branches, so that, the little balls go together, and every once in a while, some hang a right turn while others keep on going. We grow branch points off of the polymer. There's things that would be happening in the chemistry to make that happen, and that's understood, for example, by like chain transfer mechanisms and a variety of other things. Molecules can be cross-linked. So, for example, if they're sparse, we might generate gel phases that way. But you can see that when we break down the topology from this linear sequence to something that's a little bit more two-dimensional, these are objects that at any degree of conversion, right? If no matter how, if I put together n monomers in a linear sequence, and I put together N monomers with cross-links, you get the higher molecular weights, when you have cross-link structures present, right? Because like basically the same number of bonds that you're forming are going to generate, fewer molecules when we're doing cross-link motifs. And then, of course, the case of three-dimensional cross-linking, densely cross-linked networks, would be the ways in which you get to effectively, infinite molecular weights at even very modest degrees of conversion of monomer. Okay. But, how could we begin to figure things like this out? And the other part is that, polymers are not just little tiny balls that we put together. They actually have molecular structure associated with it. And those details are shown here. And so, for example, if I don't consider the case of polyethylene where everything is in fact CH2, CH2, CH2 ad infinitum, but I have a substituted monomer. So, for example, imagine the case of polypropylene, which is CH2 CH methyl, and when I make that, it goes together. And if I have a good catalyst for that, I could ask, how does it go together, right? There's two ways you could put the pi bonds together, and these are so-called, head to tail. Right, so the methyl would go in a particular preferred sequence in head to tail, as is showed, as is shown on the slide. But it could also go head to head. Well, it turns out that most really good systems for polymerization of these monosubstituted olefins tend to make essentially only the head to tail configuration. There's a few exceptions, but they're relatively few in number. So if forced to guess, head to tail or head to head, you would say head to tail, because almost essentially everything you've ever encountered or will encounter, that is true, because that's and that relates to the underlying thermodynamics associated with how the chemistry makes molecules of this type. Okay, but having said that, the structures are not flat as are shown in the depictions on the slide. In point of fact, there's stereochemistry associated with all these carbons, and we have ways in which we can draw aspects of stereochemistry, which flatten those projections in a way such that we know, where these chains are, and how they're configured, and where the side chain substituents would go, and that is in this projection form. We define these cases as isotactic, okay, syndiotactic, and atactic, and that corresponds to a case where all the alkyl groups are on one side in this projection, the case where they alternate from side to side, and of course the limiting case where in fact the dispositions are random. Now, this is actually an important issue with regard to the properties of these kinds of materials. And the reason being that if I had, as the limiting case, all isotactic or all syndiotactic stereochemistries, both of these would in fact be crystalline polymers, because in principle they could be arranged to fill space very densely in a way that's consonant with the formation of a crystalline ordered habit, right? Because they're very stereoregular in a way that would allow crystallization. Having said that, though, the syndiotactic forms would probably, in all likelihood, be cases that would crystallize in the form of helical coils. All right, and helices would in fact have very different kinds of physical properties, optical properties, morphological properties, than would essentially the same case but differing in this tacticity. Atactic polymers, on the other hand, would be amorphic, and if they form solid-like seeming stuff, it would more than likely be in fact true that these would be glasses. Okay. Now, what happens if we use mixtures of monomers, right? We get copolymers, random, alternating, blocky domains where like a bunch of A's go together, followed by a bunch of B's, and a bunch of A's, a bunch of B's, etc. And graphs, like for example, comb polymers, would be an example of a graph with very regular dispositions of where the monomers would be. It is now true that there exist chemistries to make essentially any form as is shown here schematically in great chemical diversity. And actually, copolymers of varied form are ubiquitous. And my guess is that some of you in the audience today are actually, well, at least I hope you're wearing shoes, but you're probably actually wearing shoes that the heels and soles are made out of materials that have blocky polymer structure. So if you have a sole that says Vibram on it, that's an example of a material that has that kind of microstructural motif. So for these reasons, because of how, I should say one more example. Random copolymers. There's a form of resin called ABS, which is acrylonitrile butadiene styrene. Back in the old days at the telephone company, this was the so-called black telephone polymer, a really tough material, and it was used for making telephones because you could use the handset as a hammer and drive nails with it, and it would essentially, be undamaged by the event. Telephones used to be built to last forever, and so that was a thing that was very different about the 1970s, compared to now when, we can't wait for the next iPhone to come out, and 6 months is too long to wait. So, so these kinds of microstructural details are really very important vis-a-vis properties. So, how is it that we can measure things related to morphological characteristics? So we said, like, for example, stereoregular polymers might in fact, form crystalline habits, whereas ones that have more chaotic or random chemistries or chaotic or random placements of monomer sequences might in fact not form a crystal. And and so one of the things that we can do is actually measure thermopolymers and thermal behaviors and find out whether or not changes occur that relate to the adoption of particular forms of ordered or disordered structures. So there's a plot here, plotted in terms of specific volume as a function of temperature, that illustrates, what would happen during phase transitions as temperature is changed. So as like a sample is cooled, right, density increases, right, the specific volume is going down. But if I reach a point where the cooperative motions of the components that are present there, like, sort of get frustrated and stuck, that's basically, what we're describing as the formation of a glassy state. Or in fact, what I might see is an abrupt transition, which is shown here, along this axis, along this trajectory, where there's actually a discrete phase transition, which changes specific volume discretely. That would be at the transition from the liquid to solid, right? That's the characteristic of a phase transition. And then we go along until, basically the thing gets stuck again. And so what's basically happening in this area is that we've had some transition to crystalline form, but material that's been retained in a morphic form that actually then forms a glass component. So that's a more heterogeneous structure. And then in case where a material completely is quenched and forms the crystalline phase, and then the behavior from there is also well behaved and as expected for a dense phase, just showing the normal change in density with a change in temperature. Okay, so thermal properties can be measured, and we'll see in subsequent lectures, how that can in fact be done. And part of what's interesting about crystallization versus amorphic character or semi-crystalline behavior has to do with the fact of how it is that polymers actually get into crystalline forms, and part of it has to do with the fact that it's sometimes very difficult to get a very big molecule to completely organize in an ordered habit. And so they tend to get stuck, even though thermodynamic preferences would be to have a material go completely to its most stable configuration. So it would be great to have, very thick lamellae and so that's actually shown 10 nanometers. That might be a characteristic distance that will form a lamellar sheet, which then has to have a chain fold to inject the chain back in that sheet. And so kinetic consequences when we quench polymers from melted states, so we go from the melt to solid forms or glassy forms, there could be in fact kinetic impacts because of the fact that polymers, because of their size, can get stuck in deeply quenched metastable states. And that's something that we might want to know something about and characterize in a sample of technical interest. And then we can go on and on about how crystalline habits might organize the material. This is an example of a polyethylene sample looked at under crossed polarizers. And you see these beautiful structures that show up if you look at thin films of crystalline polyethylene this way. And these are so-called spherulites, which are these domains of lamellar sheets that have basically bends in them because they also entrain some materials that are less ordered, that give them these beautiful structures that are reminiscent of the dislocations that we talked about in liquid crystalline cases. But these are actually the anisotropies associated with the organization of essentially lamellar sheets of chain-folded polymers. So many of these properties can be inferred from the characteristics seen and deduced using differential scanning calorimetry, and we'll have a lecture on that to which I will refer you. And basically, in this particular measurement, we look at heat flow in a sample that comes from how phase boundaries are being transversed, and looking at whether or not something that's going on is either exothermic or endothermic, and then we can relate that to whether or not particular states are being formed. So, for example, if we heat a material through a point where we reach the glass transition temperature, not a real phase transition of the familiar sort, but a quasi, essentially, a more complex form of what might be essentially thought of as a phase transition. The glass transition, the onset of molecular mobility, would be characterized by an endothermic heat flow. I run the sample temperature up, and I hit a temperature whereby I find that whatever is the degree of crystallinity is in the sample, all of a sudden I get a spike that's due to an increase in that level of crystallinity, which is exothermic. So what you're seeing is the heat of fusion being liberated by this onset of increased crystallization in the sample. And then I get to a place where, in fact, the sample melts. All this can be characterized very quantitatively and actually used to say, what in fact was the degree of amorphic and crystalline form present in the sample. Like, for example, by comparing that heat flow in the melt state in these crystallization phases in quantitative form. That's actually a real example of data taken from a sample of polyethylene terephthalate. And you got to just pay attention to, the conventions of, what corresponds to an endotherm or an exotherm. And that's, whether or not peaks go up or down, which is something that you could select by how you decide to define that axis quantitatively. Right, and one of the things you note is that polyethylene terephthalate is in fact a semi-crystalline polymer, but also a very good one. It's actually a material that's sometimes thought of as being not just a semi-crystalline polymer, but something that's like a quasi-liquid crystalline polymer. Has very good barrier properties, which is why it's used for soda bottles, because gas permeation rates through it are very low. Okay, vibrational spectroscopy, right? We saw the examples of how this is used to look at the molecular structures of polymers. Name this very common polymer, right? Yeah, right. So no surprise, polyethylene, right? That's the scissors deformation split due to factor group splitting. We saw that in an earlier lecture, the rocking modes, and the symmetric and anti-symmetric stretching vibrations of the methylene group, right? Very simple vibrational spectroscopy. Beautiful, right? So we can say a lot about, monomers that are present. And if we had copolymers added to this, the spectra would be correspondingly more complex. Now, here's a really interesting example of a measurement that's done to say something about the compositions of a more complex polymer. But here in a case where this is actually soluble in solution, but you could use solid state NMR techniques for more, for less solvent, for less soluble cases. And this is a polymer, polystyrene copolymethyl methacrylate, like two monomers that are included in it. And if I asked you, what is the average segmental composition of this polymer, could you tell me, in point of fact, how much of the one component and the other component is present in the sample? And the answer would be, yes, I can, right? Because it turns out that in NMR, the intensities of these peaks, scale as the number of protons that are present. So this is a proton NMR spectrum. And so if I integrate these intensities, I could then say, how much of the two components are. So like, for example, here's the methoxy of this ester group, and here's the aromatic ring. This has 3. This has 5, and if you integrate this, you would then know, very clearly, how much of one versus the other you have. And actually, if you do that, so you do the assignments of what's what in the spectra, and those are there, and you integrate it, the answer is, approximately 1-to-1. So the answer is yes, you can do that kind of assignment, and NMR is a very powerful way of doing that, right? Very precise. How about complex details of structure? Well, NMR is, again, another powerful tool for doing that. So here's three-dimensional projections of different tacticities or local tacticities associated with a styrene PMMA copolymer. And you notice that, we have different ways in which we can orient the methyl groups. The methyl groups of the PMMA segment relative to sequences of the styrene-related component, and you'll notice that this is something that I think that would be really hard to get to in any other way that I can think of. All right, from the point of view that. And these are really, really, subtle details of stereochemistry that are very local, but still relatively complex. And it turns out that all the couplings in this particular case can be fundamentally analyzed in depth and the assignments made to say what the average tacticities and probabilities are for finding sequences of any one of these forms as are shown in the schematic depiction. The real situation is basically a little bit more complex than what I've shown. I tried to simplify this in these are so-called triad sequences, and you could look further out, pentads or whatever, and that sort of level of analysis is something that can be done. However, requires a little bit of expertise in NMR spectroscopy typically. But it's good to know that such things are out there, and this is one of a few ways that exist to do this kind of really fine detail measurement on cases where samples are not possible, where there's no possibility to analyze them, for example, via diffraction methods. What else can we do? Mechanical properties are very important measures for samples, and for example, you'll hear people talk about what is the Young's modulus of the material, right? And this is something that characterizes the nature of the stress strain curve associated with a particular material sample. And as we apply a force and we measure a displacement due to that force, and we can define a relationship of stress to strain, and in the completely elastic region, the linear region of that plot, okay, that is the slope of that defines the Young's modulus of the material, and it tells us something about it. So the upper plot shows something that's like a simplified version, and like we apply a stress, we measure the strain until we get to a point where the sample breaks. Basically pull on it until it breaks, and from that we can determine certain parameters that are useful to understand that material. Its tensile strength, its elongation to break, its Young modulus. That's all quantification from mechanics. If we integrate the area under this curve, the area equals a parameter called toughness, right? And strong and tough are not the same thing. That's really an important distinction, and that is, we can put a lot of stress on something, but it can't tolerate any strain at all, and that's strong but not tough. And some things are in between, and some things, of course, are neither, right? And that's an interesting set of distinctions as exist in polymeric materials. And of course, mechanical properties can be very complex. I imagine some of you in the audience know people who have tended to chew on the barrels of clear plastic pens at some point during your time in lower grade levels. I know you don't do this in graduate school, but in lower grade levels, you probably knew somebody that did that. And if you looked at those pen barrels and those clear plastic pens, you might notice that they became foggy, and a lot of times those pens were made using polystyrene as the material, and the cloudiness that came from chewing on it is because of the generation of via mechanical processing of specific kinds of defects. And that's illustrated in the picture shown on the left, which is a computer simulation of a phenomenon called crazing. And that is, this polymer doesn't break. It actually comes apart, and it's like kind of like pulling apart, a pot of spaghetti by grabbing it, dumping it out on a table and grabbing it on both sides and just kind of pulling it a little bit, and you find that clumps of strings come apart and void spaces form. And that's why polystyrene gets cloudy like that, because of the formations of these voids. But it makes the material not very good from a mechanical perspective. A way that actually gets dealt with is to make a material that's called high impact polystyrene. And whereas polystyrene is brittle, high impact polystyrene is not, because it's a copolymer of polystyrene with a certain amount of butadiene. Butadiene and polystyrene are not compatible, so the butadiene is segregated in a rubbery phase. And these open areas, when they start to form, they actually get blunted in the rubbery phase. So it frustrates the formation of crazes, and it makes the materials actually extremely tough. Right? So that's why these compounding ideas are really important. So mechanical properties, when we measure that, give us actually the ability to characterize details like this. And these measurements are really easy. You know, we make things to grab stuff. We have ability to measure a force, and we could just use spatial fiduciary markers to look at, you know, for example, the elongation. Right, and we can look to see whether or not it's recoverable, so we can see if there's you know, plastic or elastic deformations, and fully characterize properties like this in great depth. So it's a simple measurement, but incredibly important. Okay. Mechanical properties, you know, 101, but a little bit more complicated versions of 101. I always thought it was pretty interesting, you know, to hear that there's these ultra forms of polyethylene, and that these ultra forms of polyethylene, you know, have tensile strengths that exceeds that of steel. And, you know, it's like how can that possibly be true, you know? And it has everything to do with the way in which things are physically processed. So I took a really classic paper of this kind of processing, which was followed by an X-ray measurement, and you can see the citation down below on this figure. And basically, what's being done is a polymer is being put into a tensile strain. It's being elongated. And as it's being drawn, right, we're not drawing it to the point where it actually breaks. As it's being drawn, the chains within it are actually reorganizing. And the chain structure is evolving. And what you notice is that, you know, you go from essentially powder patterns in the X-ray patterns to highly organized reflections that correspond elongation of chains and organization of lamellae. And in fact, these kinds of mechanically worked transitions in crystalline structure can be done to you know, very high degrees of elongation. Essentially, you can pull these chains to the point where they're fully extended, and the lamellae form essentially an infinite length along the axis of the drawing. So you can measure mechanical properties in that sense to say that these are incredibly strong materials, right? But you know, the understanding of the organizational states that give rise to that effect would be something that comes from diffraction and the anisotropies that the X-ray analysis illustrates are occurring, right? Really taking this down to the most discrete attributes of molecular organization in coherent form, in long-range translationally ordered forms in a crystalline phase. Okay. And finally, microscopy figures very importantly in the characterization of polymers. Right. So I show, well, the first case is actually, well, it's actually a polymeric liposome dispersed in a fluid phase, and you can see that that's a heterogeneous structure, right? But that's something that we can characterize via microscopy just by the kinds of phase contrasts that are possible. The second structure here is actually an ordered cylindrical phase in which one component's been physically removed, I believe in this case, of a diblock copolymer. And basically what's reflected in that second case is the fact that polymers have phase separated, but they can only phase separate at distances of the order of the domain size of a specific block. So the length scales are are very small in this case. You know, they're at the at the nanoscale, and because these diblock copolymers are very monodispersed, you wind up with beautiful long-ranged mesoscopic organizations that are possible to induce with these kinds of materials. Okay. We talked about imaging macromolecules before. I won't cover that. And finally, I'll note the one last provocative thought, and I put this in the context of saying, what is this thing? So you'll notice that the length scale here is actually, you know, fairly big. All right. So this is not an atomic resolution image, right? This is actually an image of something that's comprised of much larger stuff, right? And if I ask you the following question, you know, I want you to fully characterize this thing in terms of every possible attribute of descriptive structure you possibly could. You know, how would you do it? What would you apply to it? Right? You know, first and foremost, you might want to, you know, figure out like, well, what's it made of, right? And obviously, it's made of little balls, right? But you know, little balls, you know, is as far as I know, there's no spot on the periodic table for an entry for little balls, you know, and so you know they're obviously made from something somehow, and then they're subsequently organized in a particular way in which we see some degree of order. I see some places where order is lost, you know, like how would you characterize the state and organizational degree of perfection that's present in this, you know, like, you know, and so I like, for example, I see regions which may in fact have hexagonal symmetries. I see, you know, square things, you know, how would I characterize this? To answer the question, this is a colloidal crystal. It's along a fracture surface of a colloidal crystal, and you're seeing lots of aspects of structure in this. And this is a colloidal crystal formed from latex spheres, I believe. But you know, if in fact you were given the task of characterizing this in its organizational and compositional attributes, you know, what tools would you use to approach that? And I think this illustrates some of the challenging issues. Like, you know, if this was an ensemble of atoms, you know, we would have to do something that operated at atomic resolution, because that's the nature of deducing organizational states at atomic resolution, right? But this is much larger, right? And how you would do this is got to be different in some way, because this would be a very difficult experiment to do via a conventional diffraction measurement, for example. So I'll leave that as a provocative thought. At least I hope it's a provocative thought, and we'll come back and think about this in other contexts as we look at other ways that we can characterize materials. And I'll look forward to talking to you then. Thank you.